Hello everyone, I am Mads Barnkob from Kaiser Power Electronics, and today I would like to show you another Nokia Siemens Networks WCDMA amplifier. This is a little bit different from the one I showed in the three-part video of the amplifier, antenna and processing unit. This seems like a more simple unit. Maybe it's just a pure amplifier, I don't know. It seems to have 3 amplifier heatsinks, but let's take a look at it. The top of the unit is a whole cast cabinet. We have a plastic encasing with 2 fans at the back. At the front we have 6 antenna connectors. We have a DC input connector in the left side. There is 2 fiber optic connectors at the front, and we only have status lights for the fan running and a unit status lamp. At the bottom we can see we have a main heatsink up here, and we have what I suspect to be 3 amplifiers. There is a connector here which I don't know if you can see this, but this connector is used when this amplifier is used in the Flexi WCDMA system, where it connects on top of the system module or some other module in the stack of amplifiers and processing units. And just to be sure, warranty wide if broken. So I guess we will break it. So with the 3 amplifier module unscrewed, we can lift one off and take a look. These come off as small separate units. As you can see, it's HF tightened all around with gaskets. Up here at the input connectors there's an RF tight gasket. We have some small brass tight connectors around these 2. I guess this is the power inputs, and we have the output for the Diplexer to the antenna in and outputs. The whole unit itself is comprised of 2 CNC cut parts. Looks very nice. Fine edges, fine finish, looks very good. We'll take a look inside of these later in the video. Okay, the enclosure is loosened up, and I can remove this upper part. And this is the data connection module. Over here we had the optical inputs, and we have the different connectors down to the Diplexer, and there are the connectors up to the amplifier modules. So this is the controlling part, and we will also take a look at that later. Now let's get down into the Diplexer itself. So with all the screws removed, we can take off this thin cover. Okay. Again, we have some lock. Wow. This looks incredible beautiful. This is really something much more different than the other one that I had taken apart. This actually seems to, we have the power supply up here at the top, and we have, these are marked 1, 2 and 3, the 3 amplifiers. Wow, what a nice board. can't wait to really dig into this, look up some part numbers, and see if we can draw a signal path and how this works. I will get this further apart so we get down to the Diplexer and tuned cavities. So let's see. So as this is not my first RF amplifier that I take apart, you can say that I shouldn't be surprised that there were so few screws and that the Diplexer module probably was available down under here. Now that I have the main signal conditioning board loosened, we can see that this is just like any regular Diplexer, where the cavities are very tightly bolted together with all the adjustable pins for tuning the cavities up through the Diplexer for the receive and send channels. So I will get this taken further apart. I had all the screws removed. The time lapse failed me somehow to record, but nothing special was lost. It's just a huge amount of screws. Now we can remove the top plate of the Diplexer module, and what we see down here are actually a full casted cavities where the tuning cavities, where the tuning pin goes into, as we have here, are all a part of the full cast. I've seen prior in other units that these are separate units that are bolted in or screwed in. What we can see that we have this up here is the transmitting cavity, and we have, I think it's two receiving channels here, and that repeats for the 3 amplifiers that has 2 antenna connectors each. So if we take a closer look here, what I just showed was that we have one antenna that is only for, I guess it's only for receiving, and another antenna that has both a transmitting and receiving channel in the Diplexer. If we take a look at the top plate itself, we can see that it has the adjustment screws for the tuning pins, but it also has a lot of plastic things here, and it also had 3 connectors. And this is where it gets high-tech in a way I have not seen before in a Diplexer. That this is actually mounted with 3 small servo motors, and it is adjustable. All these parts that you can see that has copper on it can actually move up and down, so it is possible to remotely tune this amplifier. This is the first time I see this. With one of the motors removed, it is now possible for us to see that how the sliding action works. So what happens is that these the lighting is a little bad here, that these conductive surfaces on the plastic parts can be moved what looks like half the distance of one chamber in the Diplexer. So if this controls conductivity near the tuning pins, or it has something to do with conductivity throughout the chamber itself, I am not completely aware of that right now. We can now take a look at the central processing unit. So this is the board where we have the two optical network inputs. So this is basically the whole digital to AC converter part. Just get this free of goop. See, we have all this pink goop here. It's the heatsink compound. We have the input here, the two optical inputs. We have, let's see, 1, 2, 3, 4, and 4 CPUs. Judging on where we have the RAM, it seems like we have the central CPU over here with its 4 RAM chips, and each 2-channel amplifier have a pair of these digital to analog CPUs, and it has all the related circuitry to the output connectors. It also has the feedback input, the receiving. So this is all the sending of signals and receiving of signals that is handled by this board. Here I have one of the 3 power amplifier modules, and let's take the lid off and see what's inside. So here we have the power amplifiers in itself, the silicon and all. This is also where we find most of the gold, I can see. So if we take a look down here at the start, I will go through this more thorough once I get on the PC and can draw some lines and so. But we have the in and output here. We have some small amplifier here, so we can follow the traces up to this transistor. This is a preamplifier for the 2 large RF power amplifier transistors we have up here. It goes out in 2 parallel tracks, which is then combined again at the output, or if it's send and receive, it's simply occupying the same physical space but in different frequency domains. Up here we have a isolator or circulator that we have a signal coming in here. That signal coming in on 1 would go out on 2, but signal coming in on 2 would go out on 3, and so on. It's a magnetic. It's built up from ferrites and magnetics and isolators. It's called a isolator / circulator. But more about this amplifier board later. In the following pictures I will show you the component names and try to do a signal path analysis, and you can also view the high resolution pictures if you follow the link in the description. In the upper left corner of the system board we see a Freescale PowerQuick 2 667 MHz CPU. On the left side of this there is 2 to 16 GB of Samsung DDR2 RAM. It is not possible to see exactly how large these RAM chips are. On the right side of it is a Xilinx Spartan 2 FPGA. This controller handles all the peripheral I/O that is not directly related to the mobile antenna signals, but has more to do with monitoring and surveillance of different parts of the amplifier. On the right side, upper right side, we have the optical fiber in and outputs, and this is basically where the amplifier gets all of its data and also transmits all data out into the other parts of the network. As the amplifier itself had 3 separate amplifiers, it can also be seen on this board that there are 3 separate controllers for the analog to digital conversion and the digital to analog conversion. If we start down in the left corner, as you can see I have marked up 2 ICs with the number 4. This can be seen in 3 places on the board.
This is two analog devices, 9238 chips, which are 12-bit 64 megasamples per second analog to digital converters. These feed their output to the CPU seen as marked number 1. This is an NEC 4377408 CPU. It is not possible to find any kinds of datasheet on this CPU, but it handles the whole digital conversion of the mobile signals to be transmitted along the fiber line. If we look down in the right corner where the two output connectors are for the amplifier modules, above it we can see two ICs, one marked with 2 and one marked with 3. Number 2 is a Altera hard copy 2, which is a 350 MHz ASIC. It's basically a improved FPGA controller, and it has a highly configurable setup with nearly 2 million gates and 3 megabytes of RAM. This chip decodes the mobile antenna signal, the mobile signal coming from the CPU after it comes from the optical network. It feeds these information into the analog digital converters from analog devices 9787, which is a 800 megasamples per second digital to analog converter. The following board shows the input filtering board, which handles the signal conditioning after the signal comes from the Diplexer and before it enters the system module. Here in the overview picture we can see there is a lot of shielding, and you can also spot the 6 brown or golden cables that are connected to the board. These were connected to the system module itself. At the next picture I just want to show a few details that you can see how the shielding plates have been mounted on the board. Normally these would just be soldered to the board, but on this particular unit, as we can see on the next picture, you have 6 small clamps that holds the shielding in place, exactly like you see a fuse holder does it. With all the shielding removed, we can see the 3 amplifiers, all passive signal conditioning tracks, in the 3 fields at the upper part of the picture. Right in the middle there is a 4th shielded area, and this, I guess this is basically just controllers for all the power supplies that you can see on the rest of the board, mainly at the bottom and in between the shielded tracks. If we take a closer look at this CPU, it is a NXP Coldfire, which is a 166 MHz 32-bit CPU with external DDR RAM and a built-in 1000 Ethernet controller. Next to it is a smaller ISIS 64 MB SRAM chip. I'm not completely sure what this actually handles on this board. Taking a closer look at one of the 2-channeled parts of the signal conditioning board, we can see that there are a lot of smaller components connected all along the tracks. There are a lot of bends to make sure that the impedance of this circuit is always 50 ohm. It is highly important for such high frequency signals that the input is 50 ohm terminated, that the signal pass is 50 ohm, and that the output is 50 ohm impedance. And this is basically what you see all along these tracks. All kinds of small silver plated parts are capacitive coupled to ground, or you can also see that all the waved PCB tracks are the inductance. So all this mainly forms LC filters that ensure that there always is a 50 ohm impedance in this circuit, where there are some Anor and Singer hybrid couplers that basically makes it possible for more than one frequency bandwidth to use this amplifier at the same time. And this is also why the same mobile amplifier can receive and transmit on different mobile bands. Looking at the 2-channel amplifier module, here we first see an overview with the different parts lined out in red. What I will do is take a larger picture and record scrolling around so we can see some of all the nice features of a high frequency RF design. Here in the close-up of the 2-channel amplifier module, we can see the two input connectors, and as we can see, the signal goes up along this line into a unknown preamplifier CPU. As we can see, there are two large screws, so this is heat sinked to the silicium body beneath it. The signal goes on through a adjustable inductor, through a smaller circulator. A RF circulator is a magnetic passive device where a signal can enter into pin 1 and will always output on pin 2, but not on pin 3, and whereas a signal coming the other way can enter on pin 2 and output on pin 3, but never on pin 1 again. Next to this small circulator we have a NXP LM75A. It's a temperature sensor. The connector in the middle is the power connector for the module. Here we see the first 40-watt amplifier LDMOS chip. What is worth noticing on this board is the tracks, as it looks like a regular 45-degree cut on the bends of the PCB tracks, but this is in fact a calculated slice that has been taken off. It is the distance from the inner corner to the outer corner of a PCB track, and the one part you want to cut away, the ratio between these two has to be 0.7 ratio. This is the optimal RF design for 90-degree PCB bends. When we see small PCB tracks that are not connected to the signal path, these are capacitively coupled and will work as capacitors. At the output of the LDMOS, we can see that the tracks suddenly widened and then goes narrow again. This is a low-pass filter or high-pass filter. It certainly is a filter design, and it works as so that the ground plane underneath towards this works as the capacitance, and the track itself is the inductance, and thereby the LC filter for a filter is formed. Above we have another circulator marked WCX2, and as it seems the signal can enter on pin 1 and go out on pin 2, but anything entering on pin 2 goes to pin 3 and are shunted to ground. Passing through a couple of more adjustable inductors, we go through a Anaren-Singer hybrid coupler. The signal passes through here, and a 90-degree out-of-phase signal can go the other way. This passes through two identical 150-watt amplifier LDMOS, and once again we can see that the PCB track design are optimized for 50 ohm and also completely identical impedances. The outputs of the two amplifier chips are once again combined, as these could be two completely different frequency spans, or they could be run in parallel for double power. Going up here, and right before entering the output circulator, there is a smaller bandpass filter, which is coupled down to some resistor networks or diode networks. It's hard to make out what that really is. But looking at the output circulator, we can see that pin 1 has an output from pin 2 which goes to the Diplexer, but anything coming back from the Diplexer goes over into a 50 ohm shunt or attenuator, and if this is used for just shunting the return power or actually doing any measurements, I'm not quite sure.